10.3 Strengths of Acids and Bases. In this section, our goal is to identify strong and weak acids and bases and learn a little bit about the equations and why they would be classified this way. Now, a strong acid completely ionizes in aqueous solutions. And so you go, well, how do we represent that? Well, that's going to be one arrow going one way, which shows that the HCl plus water totally go. This H gives up its hydrogen to the water, and so this H comes here with the water. We make our hydronium ion plus our chloride ion. Whereas a weak acid only dissociates a little bit in water to form a few ions. And so you may see that these arrows look equal because they are of equal length, but please, just because they're of equal length, do not think that they are equal amounts, like this is the same amount as this. No, they just reach this point of equilibrium. And so these are going to be weak acids when they only have a little bit of the hydrogen that comes off of here to form with the water to form the hydronium ion. Now, in water, the dissolved molecules of, let's just put HA, meaning H standing for like the hydrogen in an acid, they are going to dissociate into ions 100%. So all of it will dissociate to give the hydronium ion and the anion part. So in this case, the anion part would be the I. Up here, this is just like X in your math class, but we're going to say, the conjugate partner of the acid. Now, in table 10.3, there are there lists different strengths of our acids. There's 6 common strong acids. Now, you will notice the 6 common strong acids. Some of them are your halogen acids, like the HI, HBr, HCl. Then the acids, 2 of the acids that we've learned already, sulfuric acid and nitric acid. And another one that we haven't talked about, and there's a reason why it's a strong acid, but that's a higher level chemistry, is our perchloric acid, which is 1 more oxygen than normal than chloric acid. Now, as the acids get stronger, their conjugate bases are weaker. And guess what? The opposite would be the same for the bases. Now, in our weak acids, only a few molecules dissociate, and most of the weak acid remains as this undissociated form of the acid. So over here, these concentrations are relatively small. And so you'll look at our chart that it shows that here's our beginning, we add water, and in our final product, we have mostly a lot of our original amount and a little bit of acid and the conjugate partner of our acid. And so if you compare, like, are most of the acids strong or are most of the acids weak, most of the acids make up these weaker acids. And these weaker acids actually have stronger conjugate bases. There's kind of a relationship there. Now, in an HCl solution, the strong acid HCl dissociates 100% to form HCl. So again, we're talking about strong acid. So here's our HCl. It is a concentration of 1 molar. It is going to totally dissociate into our hydronium ion concentration and our conjugate anion, the chloride ion. Whereas here we have our acetic acid, and you go, how do I know that that's a weak acid if you don't show me an equation? Well, I'll tell you how. Let's come back here. If it's a hydrogen acid, or a halogen acid, I should say, okay? It's got your H and I. All of them except HF are strong acids. Then our nitric acid and sulfuric acid are also strong acids. The only one really you have to memorize there that we haven't talked about is HClO4. Now, if it's not one of these, then we're going to classify any of the others as weak acids, because for the most part in this class they will be classified as that. So here you have this, you might not even know what this is. You know it's an acid. Why? Because there's a hydrogen in front. Now then, it's a weak acid. Why? Because it's not one of the strong acids. So that means that in the product side, you are going to have a fair amount of our original molecules left, and only a few of them disassociated into the hydronium ion and the anion portion of the conjugate acid. Now let's talk about strong bases. Strong bases are formed from metals of groups 1A and 2A. So if you look at a periodic table and look at the first column and the second column, and then if you were to put an OH, as in a hydroxide at the end, those are your strong bases. So lithium and sodium and potassium are all in that first column, the alkali metals, and you put the OH with them, that makes them strong bases. Now in the second family, the alkaline earth, if we put OH with them, barium, strontium, and calcium, in other words, all of them but magnesium, they also are considered strong bases. So for this class, if we say, identify the strong base, well, if it's in the first or second column, and if we have an OH with them, except for the magnesium, then they're going to totally disassociate into water, meaning they are going to be strong bases. Whereas weak bases are weak electrolytes and only produce a few ions in solution. And you go, well, how do I know which ones are the weak bases? Because they're not the strong bases. Now, the weak bases only produce a few ions in solution. So most of the stuff in solution is going to be sitting around and still actually going to be ammonia in our water. Now, let's see if we can identify these as strong or weak acids and bases. Press pause, see if you can do it. Okay, so first of all, A. It's a hydrogen in front, so we know A, it has to be an acid. And B, because Br is one of the halogens that's not fluorine, it is a strong acid. Okay, B. H means it's an acid. And you may go, oh, that looks like nitric acid. No, yeah, it looks like it, but it's not. It's one less oxygen. The nitric acid, it's nitrous acid. So because it's not nitric acid, it's not HNO3, it's one less oxygen, it is a weak acid. It doesn't have as many oxygens there, which adds to the electronegativity, and that's another story why, but still, it's a weak acid. Okay, the next one does not have a hydrogen first, so we're going to classify it as a base. Now, is it weak or strong? Well, if you go and look at the periodic table, sodium is in the first family, and so it's an alkali metal, so that means it is a strong base. Okay, this next one, H first means it's an acid, and sulfuric acid, it's a strong acid. Why? Because it's one of those six I kind of suggested you ought to memorize. E, this is not an acid, no hydrogen in front. You see an OH and you may go, oh, that's a base. Yep. And you may be tempted, oh, it must be a strong base because I see the OH. No. If you go and look at copper, copper is not in the first or second column. It is not a strong base. It is a weak base because copper is not in the first or second family.